This material has been reproduced and communicated to you by or on behalf of the Australian National University, in accordance with Section 113P of the Copyright Act 1968. The material in this communication may be subject to copyright under the Act. Any further reproduction or communication of this material by you must be consistent with the provisions of the Act. Do not reproduce this material. Do not remove this notice.
Okay, hi everyone. So assignment 1 has been posted online since Friday. It's due in 2 weeks. There's details about the submission online, but maybe I'll show you. The assignment on the Wattle page. It's also posted on Gradescope as well, so you should have been added to the Gradescope. If you haven't been added to the Gradescope, then send me an email. So you'll submit the assignment into Gradescope, and there's information on how to do it. There's a rubric, so each question's worth 5 marks. And yeah, depending on the question is depending on how we'll mark it. And yeah, make sure you do the correct assignment. Make sure if you're 1005, do this one. Math 6005, do this one. Some of the questions should be kind of straightforward and very similar to what you've seen in lectures or workshops, and then others are a little more challenging maybe. Drop-in sessions in the Hannah Neumann building. Every weekday, 2 to 4 p.m, there's someone there qualified to help with maths. And yeah, take advantage of it. It's on level 1. You walk into the maths building, you turn right, you walk past the workshop rooms, and then there's like the blackboard with like some seats and tables. Okay, so let's get started on the content. I think after this lecture, you should be able to answer everything on the assignment. Okay, so we're still in digital information, and we're still working on representing numbers. And so we did the integers last week, and now we're going to look at rational numbers. So remember from previous lectures, we talked about rational numbers. It's just a ratio of 2 integers. When we normally write it, we'll write it as like 2 numbers, one over the other one. And so like even if you've got a whole number, then maybe you would represent it with 6/1. And well, are you happy with that definition? Well, we gave a formal definition later, and so I'll just revise over that a little bit. So we defined this set Q, which is the 2 tuples of integers with integers that aren't 0. And so our elements just look like some number and then another number. And then if we want to actually define what the fractions are, we need to say that 2 elements are equivalent or the same if we have this property. And so this means that 2/3 and -2/3 are the same thing, -2/-3. So this is just a little bit of a revision. Of course, you can maybe consider fractions like this and then say, oh, this one's the same as this one. But in reality, the rational numbers is this set here, is like one element of the rational numbers. Okay. So that works fine when we're doing formal maths, but if we're working on a computer, it's a little bit different. So first we're going to do a little bit of motivation. So if we've got a non-zero rational number, Q, and we're going to look at scientific notation. So for any base b, we can write q equals minus 1 to the s times m times b to the n. And so q is going to be the number we're trying to represent in scientific notation. B is going to be an integer greater than 2, greater than or equal to 2. That's our base. S is going to be the sign bit. So a 0 here will obviously give you a positive number, and a 1 here will give you a negative number. We've got m, some fraction, and this is called the mantissa. And then we've got n, which is going to be the exponent, so taking the power to the base. So you're probably all familiar with scientific notation from like high school science, but yeah, this sort of formula uniquely represents conditions as long as we follow like these restrictions. So not 0, m is between 1 and b, and whatnot. So let's look at an example, 23.5. It's a positive number, so the sign bit's going to be 0. Then we write 2.35 because that's the number between 1 and 10. And then our power is just going to be multiplying by 10. Okay, some more examples. If you've got a negative number, then our sign bit's going to be 1. And then we do the same trick. We write this in a number between 1 and 10. And then we take the appropriate exponent. And then if you want to write, say, a decimal, then you're going to have to take a negative exponent. And then there's this kind of little funky thing I wrote here. So I'm saying that I can represent any sort of fraction. And since fractions can always be represented by numbers written this way, in the sense that it's got some repeating structure, then you can always write it in like an exact form like this. So for 2/3, we'd write minus 1 to the 0 times 6.6 repeater times 10 to the minus 1. But say if I gave you a real number that's not a fraction, then maybe the number of digits of m is called the precision, and so it won't be perfectly accurate, but it's still a good estimate depending on how big you make your m. Yeah, so yeah, the point here is if we want to store a rational number efficiently in a computer, we will not use the decimal digits. And we also have to have limitations on accuracy because we can't just include a massive decimal for no reason. So there's a few different ways, standard ways to do this. In the Math 1005 assignment, you go through a different way of representing numbers, but the one we're going to go through is probably, in this lecture, is probably the most standard. So if you want to represent a rational number, you can also represent real numbers as well if you want. It's called the half precision floating point. It uses a 16-bit word, and it's partitioned into 3 parts. Okay. So the first part will be the sign bit. The second part will be the exponent. The second part will be the exponent. So this is n, and then the third part is going to be the mantissa. So you'll notice we're using base 2 in this case. So we're going to store a rational number x, and we're going to represent it in this sort of scientific notation, but our base is going to be 2. Okay, so the sign bit s is stored as the leftmost bit, which is bit 15, or the 15th bit, because the first one is the 0th bit. Our mantissa is going to be a number m between 1 and 2, and it's stored as the right 10 bits. And so a nice property when we're working in a binary is your digits are only 0 or 1, and so you know that you can write it in this form, 1 point something something. So in reality, we only store this part, and we assume that there's the 1 point out the front. And then, yeah, the exponent n, we store it with 5 bits in the 14 to 10 position. And so we store it with an offset. And so this allows us to do both powers to a negative number and powers to a positive number. So the offset is, we store it as n plus 15. Let's look at an example, and it'll make things much more sort of standard to go through. Okay, yeah. First, we need to sort of talk about some other properties and limitations. So in principle, since there's 5 digits for the exponent, we should be able to have n between minus 15 and 16, but they actually use the 5 zeros and the 5 ones for special purposes. And so n is actually restricted between minus 14 and 15. And yeah, so there's limitations because we're only using a finite list of digits. Some rational numbers will be stored inaccurately, and well, some won't be able to be stored at all, even if they are small enough. This was also true for the integers, but with the integers it was kind of nicer because with our 8-bit assigned bit representation, you always knew for every integer within a range of the 0, you could represent that, whereas that's not the case with these rational numbers. And yeah, so with this sort of process, you might get pretty bad estimates depending on what numbers you're working with, but there's always the solution that you can adapt the process, make a new sort of system, but maybe requiring better precision will lead to inefficiency. Okay, so let's do an example of this half floating point. So I've written the number in hexadecimal to start with, and then I'm just going to expand it out into our binary string. So 0101 is the binary for 5. Then we split it up. So we've got S is going to be our assigned bit is 0. Our n plus 15 is going to be this number, which is equal to 21. And then our fractional part of m is going to be this number here. Cool. So now we write it out into our sort of scientific notation. We've got minus 1 to the 0 because s is 0. We look at our fractional part. We put a 1 point at the front and then write our fractional part. And then we multiply it by 21 minus 15 because we've got this offset that n is actually 21 minus 15. So this becomes 1, this becomes 6, so we have this number. Move the decimal spot 6 places because we're multiplying by 2 to the 6 and we're in the binary. So we've moved it 6 spots, and then we just expand it out and write the number, and we get our fraction. So this is 64, this is 16, this is 4, and this is 1. This 1/4 comes from this term, and the 1/16 comes from this term. Does anyone have any questions about this process? I think it's pretty straightforward. It's just a binary sort of adaptation of scientific notation, so nothing too hard. Okay, so I've talked about how it's only estimating some fractions, this sort of system. And so I'm going to give you an idea and also talk about the density, so how the numbers actually appear that you can write exactly in this half precision floating point system. So the largest number you can represent is given by this string, because we're not allowed to use 5 ones here because that's used for other purposes, and then we just write the biggest fractional part that we can possibly write in that many numbers. So we get s being 0, n's going to be 15, and then we have our fractional part. If we write this out and simplify, then we get 65,504. So that's the biggest number we can represent. If you compare this to, say, the 16-bit signed integers, then we can store every integer between this range. So it's reaching a bigger range, but the thing with the 16-bit signed integer is you can reach every integer between these two, and this is not the case when you're using half precision floating point. Okay, so the second largest number we can represent is just the same thing, but I've replaced this 1 by a 0 here. And if you do the same process, you get 65,472. And so you'll notice there's a difference of 32. So that's saying every number in between those two you can't actually represent exactly using this system. So the advantage of this system is that we can actually do some fractions, and so numbers close to 0 will be pretty well represented. So we'll go through that now. So the smallest and the second smallest positive numbers we can represent. So the smallest number we can represent that's positive is the fractional part's all going to be 0. We're going to have the smallest possible exponent, and then, well, we're making sure it's positive. So working with this, our s is 0, our n plus 15 is 1, so our n is going to be minus 14, and our fractional part's just going to be 0. Write it into our scientific notation, and we get 1 over 2 to the power of 14, which is this number here. And then I do the same thing with the second smallest positive number. So the second smallest positive number is same exponent, but just add a 1 to the fractional part right at the end. Do the same calculation, and you'll notice that the difference is 2 to the power of minus 24. So it's pretty accurate when you're close to the sort of the origin 0 at estimating fractions. So this is useful for, I don't know, engineers or something when they're working with decimal numbers. But yeah, if you need to do something more exact, then this is not going to be very functional. And so there's different systems depending on what numbers you're going to be working with, or yeah, otherwise you might have to do a sort of a slower process. The advantage of this, of course, is that it's very efficient to do calculations with. Okay, so that ends the section on representing numbers. Does anyone have any questions about this or anything? Cool, so we're going to work on modular arithmetic now, and so after we cover this part of the course, then you should be ready for the assignment completely. So I've written some sort of theorem here. It looks pretty scary. So for all z in the integers, for all d in the natural numbers, there exists a unique q and a unique r such that z can be written as qd plus r, and r is between 0 and d. And maybe some of you will recognize what type of statement this is trying to say. And so all it's doing is stating this quotient remainder theorem. So given any integer z and the positive integer d, there is exactly one way to express z in the form z equals qd plus r, where q is an integer and r is a number between 0 to d minus 1. So yeah, this is probably something that you maybe haven't seen it formally stated before, but it's something you would have seen in high school, and it's kind of how you do divisions when you're first learning them. Yeah, there's not too much to it. This q part is going to be called the quotient. So d is our divisor, z is the number we're trying to decompose in terms of our divisor, q is our quotient, and r is our remaining bit left over when we divide z by d. So maybe I'll just write up an example here. So maybe if I want to represent 19 and I'm dividing by something like 4, then we can write 19 is equal to 4 times 4. So this is our quotient. This is our divisor d. And then we've got some remainder, which is 3. So there's this slide about how we can picture Q and R. So you can think of it on a number line if we're working over the positive numbers. So we've got our number line. Maybe we've got our number Z up here. We've got D here. And all we're doing is we're finding out how many times we can go D steps until we get not enough space. And then this is our remainder. And the number of times D appears is our quotient. So these probably should be written like this, ... up to QD is the last one. Okay, so often mathematicians and computer scientists, they work, say, modulo, dividing by a certain number. So we studied the remainders, we studied the quotients, so it's useful to have some sort of mathematical notation while we're working with this. So we're going to divide, if we have a number z and we divide by d, then we're going to define q, the quotient is equal to z div d, and we're going to say the remainder is equal to z mod d. Yep, so that's just saying this is the quotient and this is the remainder. So we've got some examples here. So evaluate the following expressions. And the answers aren't too difficult, but the key step is make sure you can decompose it into this sort of quotient remainder theorem. So 87 is equal to 6 times 13 plus 9. So therefore, 87 mod 13 is equal to 9. Because our remainder, when we divide 87 by 13, is going to be 9. And then if we look at minus 100, and we want to solve minus 100 div 13, we just do the decomposition. We get minus 8 times 13 plus 4. Therefore, minus 100 div 13 is equal to minus 8, because that's our quotient. Okay, so maybe the way that you work out this Q and R is how you learnt to do division in primary or high school. So let's go through that sort of algorithm, and it'll help you when you're doing your modular arithmetic. So our input is going to be our number and a divisor, and we want to get an output, which is our quotient and our remainder. And we're we're focusing on the positive numbers for now. So we're going to set our remainder equal to the number we're trying to decompose, and we're going to set our quotient equal to 0. Then we're going to start our loop. So if r, our remainder, is less than our d, which is our divisor, then we're going to stop. So maybe if you picture this on the number line, if we have the situation where this is 0, this is d, and this is r, which is equal to z currently, then we can't decompose our z into more components of d because it's bigger, and so we stop already. So that's all that's happening there. So if it's not happening, then what we do is we replace r by r minus d. So we just take away one part of r, and then we replace q, which is currently 0, to q plus 1. And then we just repeat the loop. So just keep checking, is our new r less than d? If it is, then we stop. If it isn't, then we do this, replace r by r minus d, take away a d component, and replace q by q plus r. So that's pretty straightforward, but it's always good to be able to write the pseudocode for something. And then maybe as a little exercise, can you adjust this to cope with negative numbers? So if z was, say, minus 100, could you write some division algorithm? And I think the only thing that you have to really worry about is maybe start it with if it's negative or positive, so if it's less than or greater than 0, and then maybe the direction of this might change around. So you'll have kind of two loops running at the same time. Okay. So now we're going to introduce an equivalence class. I mentioned it on the slide when we were talking about equivalence classes, maybe at the start of last week. And it was congruence modulo a divisor d. So it's a relation, Rd, as a subset of z times z. So it's a relation on the integers. And we say that A is related to B with respect to this D if and only if there exists a K in Z such that A equals B plus KD. So the difference between A and B is a multiple of our divisor D, is all that's saying. So maybe a basic example would be if we let D equal 2, then 1 R2 is related to 3. Because their difference is 2, so 1 is equal to 3 minus 1 times D, where D is 2. And so we have some notation for this type of relation. We're not going to write RD. We're going to write that A is equivalent to B modulo D. This sort of form is just nice to work with because it's the same as when we're doing equations with equality symbols. Okay, so the way that you should be understanding this relation is two integers are congruent modulo D if and only if their difference is a multiple of D, which is equivalent to saying two integers are congruent modulo D if and only if they leave the same remainder upon division by D. Does anyone have any questions? Okay, and so I guess what we're going to try and prove is this statement here. So two integers are congruent modulo D if and only if they leave the same remainder upon division by d. So we've got to prove an if and only if, so we've got to prove both directions. So we're going to start by fixing a and b as integers and our divisor n, d. We suppose that we have that a is congruent to b modulo d, and then all we need to show, if we go back, is they leave the same remainder upon the division by d. So since a is equivalent to b, or congruent to b modulo d, that means there exists an integer k such that a is equal to b plus kd. Then we're going to do something using the quotient remainder theorem. So by the quotient remainder theorem, there exist unique integers q1 and r1, so we're decomposing b by dividing by d as well now. So we're decomposing b and we get our quotient and remainder when dividing by d. So therefore we have that a is equal to b plus kd. Then we rewrite this b into this form here, and then factorize, and we get exactly this sort of quotient remainder form that we wanted. So the uniqueness part of the quotient remainder gives that R1 is the remainder when A is divided by D. And so therefore, A and B leave exactly the same remainder upon division by D. So because A, we've got our new unique remainder here, and B, we've already got it here. Okay, so then you do the other direction. So we suppose that A and B leave the same remainder upon division by D. So therefore, there exists a Q1, Q2, and R in Z such that we have these decompositions where the R is between 0 and D. We rewrite this second equation to substitute away the R, and we get A is equal to this, remove the R, rearrange it, and so by the definition of congruence modulo D, we see that A is congruent to B because the difference is a multiple of D. So I've probably gone through that a little bit quick, but I do recommend that you work through that just to get used to these types of proofs and also modular arithmetic. Yeah, so maybe we'll look at some examples now. So a basic example is minus 17 is congruent to 15 modulo 8. And the reasoning is minus 17 minus 15 is equal to minus 32, which is a multiple of 8. Cool. Okay, so I've said that it's an equivalence class, this congruence modulo D, but I haven't really, I guess, expanded on that. So we're going to talk about that now. So if we have any integer d in n and any integer a, then the congruence class, which is the equivalence class with respect to our congruence modulo d, is defined by the integers that are congruent to a modulo d. Okay, and so maybe I'll write an example here to make it a bit clearer. If we have something like 1 and our divisor is 7, then this is the integers which have are congruent to 1 modulo 7, which would be things like 1, 8, so 1 more than 7, 15, 22. So you can keep going that way, or you could go to the negative numbers as well. So we have something like minus 6 and minus 13 and so on. So you can see that I'm just adding multiples of 7. So I've got this representative in this congruence class, and then everything that's congruent to it, modulo 7 in this case, is just some multiple of 7 added or subtracted. And so we have a lemma that RD induces a partition of this form on Z. So recall that a partition means that we've separated into different non-empty sets. The union of these sets is going to fill all of Z, and then also each of these sets is disjoint from each other. So a basic example here is if we let D be 5, then you'll notice that everything, of course, is congruent either to 0, 1, 2, 3, or 4. And that's just simply because our remainder is always going to be between 0 and 4. And maybe a good question for you to go through is, can you apply this quotient remainder theorem to prove this lemma here? And so maybe you need to say why each of these is non-empty, but that's pretty clear because they, of course, contain themselves. You need to explain why this fills all of Z, and I think that would come from the existence from the quotient remainder theorem, and then the disjointness should come from the uniqueness part. So maybe I'll write that down. This is obvious. The disjointness should come from the uniqueness of the and then sort of the covering, I'll call it. So the fact that the union of these, or the union of these is going to cover all of Z, is the existence. In the QR theorem. Okay, so when you're working in modular arithmetic, the rules are kind of similar to when you're just doing normal arithmetic, but the basic ones here are the important ones. So if we've got 4 different integers and we've got our natural number, and we have this sort of hypothesis that A and A2 have the same remainder when they divide by D, and B1 and B2 have the same remainder when they divide by D, then this implies that A1 plus B1 is congruent to A2 plus B2 modulo D. A minus B1 is congruent to A2 minus B2 modulo D. And also multiplication works well as well. So let's look at an example here. If we write 27, this is actually congruent to minus 1 modulo 7, and 36, which is congruent to 1 modulo 7. The key thing to remember is we need to be working over this same 7. You can't really change the numbers here, so change this one to a 5, and then do any sort of simple rule like this. It wouldn't work. So if we want to add 27 and 36 modulo 7, then rather than adding these two big numbers together, we can instead just add these together, and we get minus 1 plus 1 is congruent to 0. So the reason that we introduce modular arithmetic is mostly because it makes calculations much more efficient depending on what the process we're doing. So lots of crypto systems rely on number theory involving prime numbers, and the number theory contains modular arithmetic, and that allows us to do certain computations efficiently while still keeping other information secret, depending on which numbers you have. And then, yeah, so just another example, 27 times 36, that's just equal to -1 times 1 using this rule here. And so we get -1 modulo 7. Yeah, so this is the key idea of modular arithmetic. So when we're computing modulo D, we can always quickly replace a number by something which it is equivalent to, because doing this quotient remainder decomposition is pretty easy to do. There's nothing tricky going on. So this means you can simplify computations and never have to worry about doing large integers, depending on the application that you're looking for. And so, yeah, here's more examples. Instead of trying to do the negative, the subtraction, just do the simpler one and you're done. And if you want to do this complicated multiplication, just simplify the components first, and then the multiplication's easy. And then say something like this, where you're taking 803 to the power of 5. So this could be a little bit challenging if you're trying to do it by hand. But if we're working over mod 7, then this comes quite easy. Just do the quotient remainder. The remainder, when you divide by 7, is 5. Then 5 to the power of 5 is 25 times 25 times 5, which is just 4 times 4 times 5, which is 80, which is 3. So, yeah, it makes things much, much more straightforward to compute. What was that, sorry? Yeah, so this is only for mod 7. I think the key idea here is you're only interested, say, in the remainders of numbers in some settings, and so this sort of computation is much easier if you do the reduction at the start and then do the computations of like multiplying or powers or something, as opposed to taking the numbers, multiplying and doing powers, and then doing the quotient remainder. Okay, so an important problem in maths is what's called the discrete logarithm problem. So if we're given a natural number d and two numbers a and q, so these numbers are between 1 and d, so you can maybe think that these might be remainders or something, and then we want to find an x such that a to the power of x is congruent to q modulo d. And so the naive way to solve this problem is to compute a to the 1, a squared, until one of your computations produces q. But if this number here is big, and this process could go on for a very, very long time. And then you could maybe do a randomized naive solution to the problem by repeatedly selecting a number between 1 and d and compute this number and stop when one of your computations produces q. So in many situations, so in the crypto system, so maybe RSA crypto system, this number is going to be a massive prime or a massive prime, two massive primes multiplying together. I'm a little bit rusty on my crypto systems. So the point is, since this number's massive, doing all these computations is a little bit slow, and that's how the privacy on the internet often relies on this fact. So I have a feeling that we might actually go through an actual crypto system at some point in this course, but I'm not exactly sure when. And you'll actually see that one of the questions on your assignment is kind of related to this problem here. I guess the thing that I'm trying to point out here is this isn't a course on crypto systems or anything like that, so you're not going to need to know any information about those in detail. The key thing is you understand how to do modular arithmetic. Does anyone have any questions? Cool. I think that's it for today.